We continue looking at atomic properties and trying to place them in periodic table. This material you can, just a reminder. For first two atoms, hydrogen and helium, we have nucleus and outer valence electrons sitting at 1s orbital. All other atoms have slightly different picture. We have nucleus plus inner shells inside in the center of atom, and these inner shells are 1,000 times larger than nucleus. Outer valence electrons are the only electrons that play any role in chemistry. Now, because we have more electrons than just in hydrogen, lithium, these electrons interact with each other. Because electrons are negative, the interaction between electrons is always repulsive. We have repulsion between negative and negative charge. So the effective positive charge in the center is not number of protons any longer, because we have negative electrons around. Even for 1s electrons that are next to nucleus, the effective charge is slightly less because of electron-electron interactions. So instead of 3 for lithium, you have 2.7. Instead of 4 for boron, you have 3.7, and so on. So for neon, you have 9.6, even for 1s. Now, 2s and 2p electrons are shielded by 1s, so the effective charge is close to number of protons minus 2. It's not exactly that number. So the effective charge for 2s electrons in lithium is 1.3, around that value, instead of 3. For beryllium, 1.9, not exactly 2, but close enough. Then it goes higher, higher, higher. For neon, it's not plus 8 as it should be if you simply subtract 2. It's 576, still very big number. Now, 2p electrons are shielded even to larger extent, so the numbers are slightly smaller. 242 instead 2.5, 314 instead of 3.2, so on. They are the same for complete shell of neon. These orbitals that describe electron distribution in multi-atomic atom, often named Slater orbitals by the name of physicist Slater. They have form very similar to orbitals of hydrogen atom. You can see it's exponential decay from distance of electron and radius. So larger the distance from nucleus, smaller is electron density. You can see 1s orbital is going here. Here is going close to 0. Now, does it come to 0? So where the atom ends? The answer is it never ends. Exponent is never 0. No matter how big r is, you still have very low electron density left. So at which point we can say that there is the end of the atom. We should, as we did for 1s orbitals, hydrogen, select some arbitrary boundary, say 1/100th of electron per square angstrom or something like that. Very small probability. Still it will be non-zero. So what we say about size of atom, what we name atomic radius, it depends on model we are using. All numbers we are seeing in tables, in textbooks, these are human-made models. For example, covalent radius is 1/2 of distance between two atoms bound by covalent bond. Now, if there is no chemical bond between two atoms, the distance between them will be larger. This radius, that is 1/2 of the distance between non-bound, we name van der Waals radius, and it's always larger than covalent radius. But same we have ionic radii. So how change these numbers inside periodic table? First, if you have more electrons, atoms would be larger. It makes sense. In one group, on hydrogen I have 1s orbital, it will be 2s orbital for lithium, 3s for sodium, and so on, and the size of each atom periodic table will go higher. Now, in one period, when I'm coming from group number 1 to group number 2, we have increase of effective charge from group number 1 to group number 2. Effective charge of lithium we have seen is around 1, for beryllium is around 2, so electrons will be closer to nucleus, and size of beryllium atom is smaller than lithium atom. The same trend will continue all the way to the end of period. Boron is smaller than beryllium, carbon is smaller than boron, and so on. At the end, this change is very small, but still visible. The smallest atom in second period is neon. Same trend is in the next period, and next period, and next. Always the size of atom is going down through the main groups of periodic table. Now, when we remove one more electron, going from Fe2 plus to Fe3 plus, size drops down. The trend in one period and one group is still the same. So lithium is the smallest in group number 1. Lithium ion is the smallest in group number 1. Sodium is larger, potassium is larger, rubidium is larger, cesium is even larger. Same is true for negative ions. Fluorine is the smallest among group number 7, halogens. Fluoride is the smallest of negative ions. Now, what we can say about energy. It takes some energy to remove one electron. We name this ionization energy. To remove the second electron, it takes much more energy because we are removing from positive ion, and this will be second ionization energy. Ionization energy is the energy required to remove an electron from isolated gaseous atom, like that. Successive ionization are possible until no electron left. Trends in ionization energy opposite to trends in atomic charge size. So helium is smaller than hydrogen. Ionization energy of helium is larger. Beryllium is smaller than lithium. Ionization energy is larger. Going up, going up, all the way to neon, very high ionization energy, then dropping down to sodium, continuing to argon. Let's look at numbers. Ionization, the only ionization energy for hydrogen is 1300. For helium, it's almost 2400, and the second is above 5000. For lithium, again, we are dropping down to 500, but the second, to remove electron from 1s level, it takes enormous energy. So very quickly we are coming to ionization energy of 100,000 kilojoule per mole. That's a very large number. And here we see periodicity increase, 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 starting new period, drops down, and then increase again. There are some irregularities. For example, nitrogen has very stable state. One cell, 2s electrons, is completely occupied, and 3 electrons are sitting separately at 2p orbitals. They are separated as far as possible, so this is island of stability. When you are removing electron, you are reducing this stability. So ionization energy of nitrogen is relatively large. Oxygen, contrary to that, has stabilized positive ions, so ionization energy of oxygen is relatively better. Same story was for boron. Now what happens when we add electron to atom? This energy we name electron affinity. It's energy associated with addition electron to gaseous atom or ion in its ground state. Again, it's all in gas state. Addition, one electron of neutral atom is exothermic for nearly all atoms. So atoms want to take electron, but to take a second electron always requires some energy. Let's look at these affinities. Helium has positive affinities, so it's unfavorable. Surprisingly, the largest positive affinity is for second group, beryllium, magnesium, calcium. The atoms who love to take electron the most are 7 group, fluorine, chlorine, then bromine, iodine. Successive, again, is always positive. So oxygen atom wants to take 1 electron, it's negative number, but oxygen ion, when it takes Second electron has positive electron affinity. Net energy for two electrons is large positive number. Again, we are talking about hundreds of kilojoules per mole.